On November 5th, 2018, a spacecraft built more than 4 decades earlier crossed an invisible line 11 billion miles from Earth, and in doing so, it handed scientists a set of numbers that didn't match anything they had predicted. This wasn't a small correction to an existing theory. This was a moment where researchers looked at fresh data streaming in from the edge of the solar system and realized their models of how the sun's bubble meets the galaxy were, in several important ways, simply wrong. This is the story of that crossing, why it caught so many scientists off guard, and why a machine older than most of the people studying its data is still rewriting the textbooks today. To understand why the crossing was such a shock, you first have to understand what scientists thought they already knew. Our sun doesn't just sit quietly in space. It constantly blows out a stream of charged particles called the solar wind, and that wind inflates a kind of bubble around the entire solar system, a region called the heliosphere. Inside that bubble, conditions are shaped by the sun. Outside it, conditions are shaped by the wider galaxy. The boundary where those two environments meet is called the heliopause, and for decades, it existed mostly as a theoretical line on a diagram, something calculated from models, rather than something anyone had actually touched with an instrument. To understand why the crossing was such a shock, you first have to understand what scientists thought they already knew. Our sun doesn't just sit quietly in space. It constantly blows out a stream of charged particles called the solar wind, and that wind inflates a kind of bubble around the entire solar system, a region called the heliosphere. Inside that bubble, conditions are shaped by the sun. Outside it, conditions are shaped by the wider galaxy. The boundary where those two environments meet is called the heliopause, and for decades, it existed mostly as a theoretical line on a diagram, something calculated from models rather than something anyone had actually touched with an instrument. For most of the 20th century, everything scientists believed about that boundary came from indirect reasoning. They knew roughly how fast the solar wind traveled. They had rough estimates of how dense interstellar space might be, based on how starlight and cosmic rays behaved as they passed through it. From those pieces, researchers built mathematical models predicting where the sun's influence should end and the wider galaxy should begin. But a model built from indirect clues is still just a guess dressed up in equations, and there's a very real difference between calculating where a boundary should be and actually flying a spacecraft through it with working instruments recording what's really there. Voyager 1 became the first spacecraft to cross that line back in August 2012, and its arrival there was treated as one of the great milestones of space exploration. But there was a catch that didn't get nearly enough attention at the time. Voyager 1's plasma instrument, the device built specifically to measure the temperature, density, and flow of charged particles, had already failed years earlier, long before the spacecraft even reached the outer planets. So when Voyager 1 actually crossed the heliopause, it crossed blind in exactly the one measurement scientists wanted most. Everything they learned from that first crossing had to be pieced together indirectly, using instruments that were never designed to answer the plasma question directly. That's what makes the second crossing, Voyager 2's crossing in November 2018, such a different kind of event. Voyager 2's plasma instrument was still alive. For the first time ever, a spacecraft crossed the edge of the solar system while carrying a fully working sensor built to measure exactly what was happening on both sides of that boundary in real time. And what it recorded surprised almost everyone who studied it. The first jolt came from the sheer structure of the boundary itself. Based on theory, scientists expected the heliopause to behave like a fairly narrow, sharp transition, something you could almost draw as a clean line separating two regions. Instead, Voyager 2 detected a wide, complicated buffer zone stretching roughly 100 million miles, sitting right at the edge of what should have been pure interstellar territory. Inside that zone, particles from outside the solar system were already mixing with material from inside it, well before the spacecraft technically crossed over. It wasn't a wall, it was a blend. The second jolt had to do with distance, and this one left several senior scientists on the mission genuinely puzzled. Voyager 1 crossed the boundary at about 121.6 astronomical units from the Sun during a period when the Sun was highly active. Voyager 2 crossed at about 119 astronomical units during a period when the Sun was unusually quiet. Given how strongly solar activity was expected to inflate or shrink the size of the heliosphere, those two numbers should have been meaningfully different. They weren't. The heliosphere appeared to be almost the same size, regardless of whether the Sun was roaring or resting, and nobody on the mission had a confident explanation for why. The third jolt came from temperature. Inside the heliosphere, the solar wind is extremely energetic, moving at speeds that translate into extreme temperatures by the standards of plasma physics. Scientists expected a gradual decline in that temperature as the spacecraft approached interstellar space. What Voyager 2 actually measured was a sharp, sudden drop, happening in a much tighter span than the models had predicted, as though the spacecraft had stepped through a much more defined thermal wall than anyone anticipated. And then came the density numbers, which turned out to be some of the most important measurements ever taken this far from Earth. Combining Voyager 1's readings with Voyager 2's gave scientists their first side-by-side comparison of interstellar plasma density from two separate points in space. What they found was that the plasma sitting just outside the heliosphere is more than 40 times denser than the solar wind plasma near the boundary. Space between the stars, it turns out, is far from empty, and thanks to Voyager 2's still working instrument, researchers finally had a direct measurement of the interstellar plasma's temperature, somewhere between 30,000 and 50,000 degrees Kelvin. That number mattered enormously because it was roughly half of what earlier theoretical models had estimated. An entire generation of assumptions about the temperature of interstellar space had to be revised because one instrument on one spacecraft happened to still be functioning at exactly the right moment. But the single discovery that stunned researchers the most, the one that the Voyager program's longtime chief scientist called the most remarkable result of the entire crossing, was this: the boundary leaks. It isn't sealed. Material moves across it in both directions. Voyager 1, years earlier, had picked up hints of interstellar particles pushing inward through the boundary before it even crossed. Voyager 2, arriving from a completely different direction, detected something else, a steady trickle of particles from inside the heliosphere leaking outward into interstellar space before the spacecraft had technically crossed over itself. Two spacecraft, two different approach angles, 6 years apart, and both of them found evidence that this supposedly clean edge of our solar system is closer to a coastline than a wall, constantly exchanging material with the environment beyond it. Put simply, the picture scientists walked away with after November 2018 was not the tidy, well-defined boundary they had spent decades modeling. It was something far messier and more dynamic, a zone where the sun's influence doesn't simply stop but tapers off unevenly, bends, thickens, and bleeds material back and forth with whatever lies beyond. 5 separate scientific papers describing these findings were published together in the journal Nature Astronomy in November 2019, and taken together, they amounted to one of the most significant course corrections in the modern study of our solar system's outer structure. It's worth pausing on just how unusual it is for a group of experienced scientists to describe their own findings using words like surprising, unexpected, and remarkable. Researchers who have spent entire careers building and refining models don't reach for those words lightly. When 5 separate papers, each covering a different instrument or a different angle of the same crossing, all independently arrive at the conclusion that reality doesn't match prediction, that's not a minor footnote. That's a signal that an entire field needs to go back and rework some of its basic assumptions. And that's exactly what happened. In the years since 2018, researchers have been building new models of the heliosphere's shape, size, and behavior using Voyager 2's numbers as a correction against everything that came before. What makes all of this even more remarkable is how it happened. Voyager 2 wasn't originally built to specialize in this kind of discovery. Its instrument survived by circumstance, not by design intent aimed specifically at outliving its twin. When the Voyager mission was planned back in the 1970s, the entire idea behind sending 2 spacecraft instead of 1 was to avoid relying on a single data point. One spacecraft could only describe conditions from one location at one moment in time. 2 spacecraft, launched on different trajectories, crossing the boundary years apart from different directions, could begin building an actual picture of what the edge of the solar system looks like, rather than a single snapshot. What nobody could have planned for was which spacecraft's key instrument would still be operating when the real discovery moment arrived. Voyager 1's plasma detector failed decades before its crossing. Voyager 2's plasma detector held on, still transmitting clean data more than 40 years after launch, right at the exact moment scientists needed it most. It's a strange kind of luck, built into a mission that was carefully designed to minimize the role luck could play, and yet luck still ended up mattering enormously. Consider, too, the sheer scale of what Voyager 2 had already accomplished before it ever reached this boundary. It remains the only spacecraft in history to have flown past all 4 of the outer planets, Jupiter, Saturn, Uranus, and Neptune, using the gravity of each one to slingshot itself toward the next. At Uranus in 1986, it discovered 10 previously unknown moons, found 2 new rings, and measured a magnetic field so strangely tilted from the planet's spin axis that scientists are still trying to fully explain it. At Neptune in 1989, in what remains the only close flyby of that planet ever conducted, it discovered 6 additional moons, clocked wind speeds faster than anywhere else recorded in the solar system at the time, and photographed active geysers erupting from the surface of Neptune's largest moon, Triton, evidence that Triton was likely captured from the outer solar system rather than forming alongside Neptune itself. By the time Voyager 2 reached the Heliopause in 2018, it had already spent 41 years in space, using technology designed before personal computers, before cell phones, before the internet existed in any recognizable form. and it was still functioning well enough to deliver the single most important plasma dataset in the mission's history. None of this is finished. Both Voyager spacecraft are still active today, still sending data back across billions of miles, and both are still running on a slowly fading power source. Each spacecraft carries a set of generators that convert the heat released by decaying plutonium into electricity, and that decay is steady, predictable, and impossible to stop. Every year, each spacecraft loses a small, fixed amount of available power. Engineers have spent years carefully shutting down non-essential systems to stretch out what power remains, prioritizing the instruments most likely to keep delivering unique science. As of this year, Voyager 2 still has 3 working science instruments, including the plasma detector that made the historic 2018 measurements possible. That's actually one more functioning instrument than Voyager 1 currently has, since one of Voyager 1's remaining instruments was shut down earlier this year to conserve power. Because Voyager 2 has a slightly larger power margin, engineers have chosen it as the test case for an ambitious and risky new procedure designed to reorganize how power flows through the spacecraft's remaining systems all at once, in hopes of buying both probes more operational time. If that attempt succeeds, a similar procedure is expected to be tried on Voyager 1 later this year. Why does any of this matter beyond the raw curiosity of it? Because there is currently no other way for humanity to directly sample the region where our solar system ends and interstellar space begins. No other spacecraft is anywhere near that distance. Nothing else currently under construction will get there for decades, if such a mission is ever built and funded at all. Every additional month that Voyager 2's plasma instrument keeps working is a month of direct, on-site measurement of an environment that cannot be recreated or simulated with full confidence from Earth. Once these instruments go silent, the record they've been building simply stops, and whatever questions remain unanswered will stay that way until some future mission, not yet designed, not yet funded, eventually retraces the same path. And there are still real questions left open. Why does the Heliopause sit at nearly the same distance from the Sun, regardless of how active the Sun is? What actually causes particles to leak across the boundary in both directions, and does the rate of that leakage change over time? What is the true overall shape of the heliosphere itself? Some models suggest a long trailing tail, similar to a comet, stretching away from the Sun's direction of motion through the galaxy. Other models suggest something closer to a rounded, almost teardrop shape. Voyager 1 and Voyager 2, having crossed the boundary from 2 different directions, are currently the only 2 data points scientists have for testing which of these models is closer to correct, and every additional reading either spacecraft sends back helps narrow that answer down further. There's also the deeper question of the interstellar magnetic field itself, something both spacecraft have measured from their own separate vantage points. The direction and strength of that field carries information about how our entire solar system is oriented relative to the much larger magnetic structure of the galaxy as a whole, a structure that is still not fully mapped or understood. Voyager 2's magnetometer, still operating in 2026, continues to contribute readings from the southern side of the heliosphere, a different angle than the data Voyager 1 has been sending back from the north. Behind all of these scientific questions sits a small team of engineers at NASA's Jet Propulsion Laboratory who have kept both spacecraft alive for far longer than anyone involved in the original 1970s mission ever expected. Many of the engineers who built and originally operated these spacecraft have long since retired. The people running the mission today had to learn command systems, programming approaches, and engineering conventions from an era before most of them were even born, simply to keep communicating with hardware that predates almost every technology we take for granted now. Every command sent to either spacecraft takes more than 16 hours just to arrive, and any response takes another 16 plus hours to travel back, meaning a single question and answer exchange with either machine takes well over a full day to complete. Despite all of that, in the summer of 2026, that small team is still sending commands across roughly 13 and 16 billion miles of space, still waiting more than half a day for each reply, and still finding ways to squeeze a little more science out of 2 machines that were only ever designed to operate for 4 years. What Voyager 2 found when it crossed the Heliopause in November 2018 wasn't just a confirmation of existing theory. It was a genuine surprise, a set of measurements that forced scientists to rebuild parts of their understanding of how our solar system actually meets the rest of the galaxy. A boundary that was supposed to be a clean, sharp edge turned out to be a wide, leaking, unevenly structured zone where material moves freely in both directions. A distance that was supposed to shift dramatically with solar activity turned out to barely move at all. A temperature that was supposed to be roughly known turned out to be off by nearly half. All of it captured because one aging instrument, against long odds, was still working at exactly the moment it needed to be. The data keeps coming in, even now, faint and delayed by more than 16 hours of travel time, carrying information from a region of space that no other instrument in human history has ever directly sampled. And as long as that signal keeps arriving, there's a real chance that the next surprise from the edge of our solar system is still waiting to be found. It's easy to forget, watching all of this unfold in headlines and journal papers, that every single number in this story is coming from a machine that was expected to stop working before most people currently reading about it were even born. Voyager 2 wasn't built with interstellar plasma measurements as its primary goal. Its main assignment was the grand tour of the outer planets, and everything it has done since crossing the Heliopause has been, in a sense, bonus science, squeezed out of hardware that has already vastly outlived its original mission plan. That's part of what makes the 2018 crossing so remarkable. It wasn't the result of a purpose-built interstellar probe designed from scratch for this exact job. It was the accidental second act of a planetary flyby mission that happened to still be alive, still pointed in the right direction, and still carrying one working instrument at exactly the moment humanity needed it most. There is no guarantee that moment repeats itself. The power keeps fading. The instruments keep aging, and somewhere down the line, whether in 1 year or several, the signal from Voyager 2 will eventually go quiet for good, along with whatever discoveries it might still have been capable of making. Until that happens, though, this aging spacecraft remains humanity's only working eyewitness to the true edge of our solar system. And every new transmission it sends back has the potential to surprise scientists all over again, the same way it did on that day in November 2018 when the numbers came in and nothing quite matched what anyone had expected,